In this lecture, I want to briefly go over a really interesting observation that was made by Belinsky and Laricki in their recent book on voting theory. They asked the question, is selecting a group ranking or designating winners simply two sides of the same coin? At least on the face of it, it seems like the answer should be obviously yes. So if I give you a method of selecting a group ranking, so the idea here is you take all of the data that the voters provide you, all of the rankings provided by the voters, and you look at that data and you find an ordering that is the best compromise given all of the rankings in the data. Then, once you've identified this group ranking, then simply the candidate that's ranked first in this group ranking is declared the winner. Whoever's ranked second comes in second, and so on. On the other hand, if I give you a method for identifying winners in an election, you can easily turn that into a method to find an overall group ranking. So we determine who the winner is. That person is going to be ranked first. We remove that person, that candidate from or alternative, and we run a sub-election without that candidate. And whoever wins that smaller election comes in second, then we can find the third place candidate, and so on. So it really seems that these are just two sides of the same coin. Now, Belinsky and Laricki point out that that's not quite the case. So before we do that, we need to come up with some methods that are good at finding overall group rankings and methods that are good for selecting winners. So we'll use board account to select the winner, but what about a method to find a good overall group ranking? Well, here we're going to draw on an idea of Kemeny. So Kemeny defined the distance between two rankings, two linear orderings, and we're going to use Kemeny's rule, and this is going to associate a score with each possible linear ordering over the set of candidates. And the idea is that a voter is going to contribute k points to a ranking if his input agrees in k pair by pair comparisons. So remember, the Kemeny distance is going to be the fewest number of swaps you need to turn one ranking into another ranking. So a voter then is going to contribute, if there are n total candidates, is going to contribute n minus the Kemeny distance between his ordering, his ranking, and the ranking under consideration. The Kemeny score then of a ranking is just going to be the sum of all possible points over all voters, and the Kemeny ranking is the ranking that maximizes the Kemeny score. So the question is Borda's method good for designating a winner or finding a ranking or both? And is Kemeny's method good for designating a winner or a ranking or both? Well, let's look at an example. So Belinsky and Laricki point out this example right here. So we have a Condorcet triple right here with 3 voters ranking A above B above C, 3 voters ranking B above C above A, and 3 voters ranking C above A above B. And then we have this one voter which we can think of as the tiebreaker. This one voter ranks A above C above B. And naturally, just given the data, one natural way to understand what's going on here, we would say that A, B, and C are tied given this sub-election. Then this one voter comes in and breaks the tie in favor of A. So A will be declared the winner according to board account and many other voting methods out there. But what is the most natural group ordering given this data? Well, according to Kemeny, we can calculate, so here are all the possible linear orderings over the 3 candidates, and we can calculate the Kemeny score for each one of those orderings. And we see that A ranked above B ranked above C, and C ranked above A above B have the highest Kemeny score. How do you calculate that? Well, note, these 3 voters each contribute 3 points to the ranking A above B above C. So that's 3 times 3, which is 9. What about these 3 voters? Well, they each contribute 1 point. So that'll be 3 times 1. What about these group of 3 voters, they will each contribute 1 point because the ordering C above A above B agrees on one pair-by-pair comparison with A above B above C. So they also contribute a total of 3 points. And then this last voter contributes 2 points. 1 times 2. And that's because the ordering A above B above C agrees in 2 pair-by-pair comparisons with A above C above B. The total is 9 plus 3 plus 3 plus 2, which is 17 overall. Now you may want to pause the video to make sure the rest of my calculations are actually correct. The important point is that A over B over C and C over A over B are tied, and Kemeny identifies those as the best group ordering, or the most natural, whatever the group ordering should be. It should be one of those 2. So let's take a look at what we have. We have the Borda ranking gives us, if we just calculate the Borda score for each of A, C, and B, we see that candidate A is going to come out on first, candidate C is going to come out second, and candidate B is going to be ranked third. So A has the highest Borda score, C has the second highest Borda score, and B has the lowest Borda score. And that's natural because this group right here, if we just looked at the Borda score for the 9 voters, we will see that A, B, and C each have the exact same Borda score, and then this one voter breaks the tie. So naturally, the Borda ranking is going to align with that one voter. Kemeny tells us that the 2 possible best group orderings are A above B above C, and C above A above B. And so what Belinsky and Laricki pointed out is they said, well, think about it. No reasonable ranking function must choose A above C above B. Because there we're imagining the orderings as one unit. And note, there's only one person in the entire society that ranks A above C above B. So why should the very small minority, and we can multiply the number of agents to make this a very, very small minority, why should that one person dictate what the group ordering, the overall group ordering should be? So that means that the Borda ranking is out. The Borda ranking does not give you a good overall group ordering. On the other hand, they point out that any reasonable ranking derived from a winner selection function should select A above C above B. And the intuition there is, according to these 9 voters, A, B, and C are all tied. So this last voter we think of as the tiebreaker comes in and breaks the tie, and naturally the winner, so the ranking that is derived from the winner selection function will be A ranked above C ranked above B. However, Kemeny does not actually choose A is above C above B. Kemeny chooses A ranked above B ranked above C, or C ranked above A ranked above B. So according to Kemeny, if we use Kemeny to designate a winner, we will either select A or we'll select C as the winner, and that depends on the tie-breaking rule. And B or A will come in second, again, depending on the tie-breaking rule. So they use this observation to point out that there is a fundamental incompatibility between electing, choosing a winner, and ranking, finding the best, the ideal group ranking.